Hi everyone, I'm Dr. Syed Mustafa Safavi, a cybersecurity researcher and academic with a focus on AI, system architecture, and digital security. I'm joined by Sarah Johnson, a tech entrepreneur and strategist working across emerging technologies. In this podcast series, we combine academic insight and real-world practice to explore critical topics in tech and innovation. Whether you're a student, professional, or enthusiast, you'll gain a balanced perspective grounded in both theory and application. Make sure to subscribe, follow, and join us on this journey as we unpack the future of technology, one episode at a time.
Welcome everyone to our discussion on memory management in computer systems. Today we're diving into how physical and virtual memories are handled, how processes share and allocate memory.
Absolutely. It's a fascinating topic, especially when you consider the challenges that come with managing memory effectively.
Right. And one of the central ideas here is that memory management is basically about organizing programs and data in memory, ensuring that processes find the space they need to run smoothly.
Yep. And it's all about maximizing memory usage so that we reduce waste, isn't it?
Exactly. And to achieve that, we rely on techniques such as single tasking with overlays, fixed partitioning, and variable partitioning. It's like designing the blueprint for how memory is split up and used by different processes.
Right? And that's where things like overlays come into play. They allow a process to be larger than the physical memory by loading in only what's needed at any given time.
Yeah, it's like imagine you're watching a play. You only set up the stage with the props for each scene instead of cluttering the whole stage with everything all at once. That's what overlays do.
Yeah?
They swap in instructions as needed while deallocating the old ones.
That's a neat analogy, but doesn't this approach have its limitations, like not leveraging additional memory if it's available?
Precisely, that's one of its downsides. Even if you have spare memory in the system, the overlay design restricts a process to only use what's planned, which can limit performance if the process could benefit from more memory.
Right, that limitation really brings out the trade-offs in memory management strategies.
Moving on, another key part is memory partitioning. Now, there are two main flavors here: fixed partitioning and variable partitioning. In fixed partitioning, the memory is divided into constant-sized slots.
And each partition can hold, only one process at a time, which means the total number of processes that can run simultaneously is limited by the number of partitions available.
Exactly. It's a simple approach, but it comes with its own issues like internal fragmentation, where extra memory allocated that isn't used causes waste.
And that's where variable partitioning tries to step in, right? Here, the operating system allocates memory on the fly based on the process size, using methods like first fit, best fit, or worst fit algorithms.
Yes, exactly. With variable partitioning, when a process arrives, the system searches for a well-fitting block of memory. It's like trying to find the perfect puzzle piece for the process.
Although variable partitioning has its own drawbacks, namely external fragmentation. As processes load and unload, you can end up with these scattered little bits of unusable memory.
It's frustrating because small pieces of free memory might be left behind. So even if the total free space is large, it might not be contiguous, and the process can't be loaded.
Yep, and that's often resolved with compaction, a process of shuffling memory around to form one large contiguous block.
Precisely. Though compaction itself can be resource intensive, if you're constantly moving stuff around, it could slow things down.
But don't you think that sometimes the trade-off is worth it, especially in systems where achieving maximum memory utilization is crucial?
That's a good point. I do think that while compaction adds overhead, in scenarios where fragmentation becomes a major bottleneck, it can be absolutely necessary.
Right, and it's even more interesting when you compare that with fixed partitioning, where internal fragmentation is the big concern, as opposed to the external fragmentation seen in variable partitioning.
Yes. Internal fragmentation happens when a process doesn't fully utilize the memory allocated to it. It's like ordering a large coffee and only drinking a quarter of it, leaving the rest wasted.
That's a funny but accurate analogy. And also, with fixed partitioning, each partition size is predetermined. So if a process is smaller, the extra space is wasted and can't be used for another process.
Exactly. And what's interesting is that even though fixed partitioning is more straightforward, it does inherently limit how many processes you can run based purely on the number of available partitions.
Yeah, that introduces constraints on multi-programming. The degree of multi-programming is directly connected to those fixed slots.
Precisely. It's all about finding that balance between simplicity and flexibility in memory allocation. You want to keep things simple enough for programs to load efficiently, but also want to maximize memory usage, right?
Yeah, for sure. And then there's the whole idea of logical versus physical memory. The CPU generates logical addresses which are then translated to physical addresses seen by the memory unit. That translation is crucial for correct operation.
Right. It's almost like having a map. The logical address is like an address you understand, and the physical address is where it actually is located in memory. It abstracts the complexity from the program's perspective.
That translation process, managed by the memory address register, is essential for the entire operation of processes.
Exactly. And it helps in efficiently loading and executing processes. But let's circle back to something we touched on earlier, the single tasking with overlay technique.
Right. I find it particularly interesting because it essentially lets a process exceed the physical memory size by loading portions of the process dynamically, right?
Yes, it's like having a bookshelf where instead of bringing the whole encyclopedia out, you only take the volume you need at the time and swap it out when you're done.
That's an interesting way to describe it. But I do wonder, isn't it a bit inefficient if the process could actually use more memory if available? Why not just load it all at once sometimes?
That's a fair critique. However, the design goal here is often to work within systems where physical memory is limited. So overlays are a practical solution despite their inability to leverage extra memory.
True, it's a compromise, but one that's sometimes necessary.
And before we wrap up, let's briefly run through the key terms you really need to master. Single tasking with overlay, fixed partitioning, variable partitioning, internal fragmentation, and external fragmentation.
Yes, those are the building blocks. And understanding how they interact really helps in grasping the bigger picture of computer architecture and operating system management.
Exactly. It's all about designing a system that, makes memory as efficient as possible while balancing the need for flexible process management.
And as we've seen, each technique has its own benefits and drawbacks. The key is to be aware of these trade-offs when designing or studying a computer system.
Right? And whether it's through overlays to manage larger processes or using various partitioning methods to allocate memory, each approach plays a crucial role in making sure that memory is managed effectively and waste is minimized.
Absolutely. It really highlights the intricate balancing act that operating systems need to perform to keep everything running smoothly.
And as we look ahead, the next steps in our exploration will take us into process management, which builds directly on these ideas of memory allocation and efficiency.
That sounds like a great follow-up. I'm looking forward to diving deeper into how processes interact with these memory management techniques in real-life applications.
Me too, and thanks for the engaging conversation today on such a complex but crucial topic.
Certainly, thanks for all the insights. Catch you next time as we explore more of these system fundamentals.